Hello everybody, today I'm gonna talk about Lyapunov function computation using LP, which means linear programming. But before that, let me expand on the SDP subject that I covered in the previous video, right? And for that, I'm going to first explain step by step how would you prefer to parameterize Lyapunov function. Okay, all right, this is the first thing that I'm going to cover right here. This is the Lyapunov function. So let's take a couple of step backs and let's remember why we are doing this in the first place, right? We have a nonlinear system and we are given probably one equilibrium point, right? One equilibrium point, and it might be global stability, but let's first focus on global stability subject, right? We, for example, x1, x2, of course there might be other states, yeah, but to be able to visualize what I'm trying to say, I'm going to cover for two-dimensional nonlinear dynamical systems, right? Okay, and here this is the equilibrium point, right? And we want to prove the global stability. Okay, so to be able to prove global stability, or to be honest with you, you would run a bunch of simulations in most of the cases, right? But Lyapunov function is kind of there to be able to say, hey, this is global stability and Lyapunov function is my certificate, like certificate is in the optimization case, right? So in that regard you would need Lyapunov function, but of course you might not know if, for example, you might run 1,000,000,000 simulations, but your problem or your nonlinear system may be that problematic, and even though the simulations that you ran were showing that the convergence to the equilibrium points, but it might not be the case for the initial points that you haven't sampled in state space, right? So yeah, that's why you would like to at least have a Lyapunov function. And okay, so for that you will need a Lyapunov function. And remember the properties of Lyapunov function. First, v of x must be positive definite. Let's not focus on the asymptotical stability. Let's just first focus on the stability in the sense of Lyapunov, right? And for x not in x in some domain, right? But not doesn't include 0 or 0 the equilibrium point. Okay, and second condition that we would like to have our Lyapunov function to be okay 0 less than 0. Okay, again for x not including 0. All right, so, and in the previous video we talked about this condition. Sufficient condition for this proposition or this condition can be given by v of x in right sigma sub x s, sorry, and that representation stands for SOS, sum of squares, right? And if you have something which consists of square terms, right? For example, f1x square, f2x square, dot, right? But all of them are square of some expression, right? You would know that, yeah, that's obviously also definite. So that is the kind of rationale behind this, sufficient condition. And again, for the negative definiteness of the, or negative semi-definiteness of the v dot term, right? You would again have that type of sufficient condition, right? Sigma sub s again stands for sum of squares. And I'm sorry, by the way, let me just put minus there because it's important, right? V dot is less than 0, right? Minus V dot is greater than 0, right? And sum of squares condition can be implemented for that type of condition, right? Okay, let me just delete all of them, right? So V being positive, V dot being negative, meaning we could be able, we could find, or let me say it this way, we want to parameterize V such that it would be easier for us to represent V of x in sum of squares, right? Sum of squares is a sum of square function. So for that we are just going to use this type of representation. This is like the maybe this is the representation that you would like to use if you were to attempt solving this problem. This type of selection would be your first one, right? And okay, let's look at what m1 is. M1 is the basis function. Normally you would start from 1. By the way, 1 means okay, let me just get that over with. 1 sec. 1 kind of means x to the 0, right? And let's say we have only x, one dimensional system, right? And that means x to the 1, okay? X square means x to the square, right? Dot dot dot. Let's say we have two-dimensional system, right? But before that, if we have 1, that would kind of complicate our problem because for example, we are going to impose this constraint, and if, right? So the coefficients, we are going to parameterize this v of x, and coefficients that corresponds to that basis function, that term, right? And will be 0. So in that case we shouldn't include 1 or the x to the 0 basis function, because we would just increase our dimension of the problem, and those parameters will be 0. We know that it would complicate our problems, and you wouldn't usually increase the dimension of your problems, because this is, of course, we're going to be focusing on the simple systems, but maybe like 10-dimensional systems in the future, hopefully we might get, and in that you will start to get some type of numerical ill conditioning type of optimization problems, usual optimization problems. So that's what I'm trying to say. You don't increase the dimension of your problem without having a very good reason, okay? And adding a 1 is not a good thing, is okay, end of the story. And yeah, let's focus on two-dimensional system. For example, we set x squared, x to the 3, right? X to the 5, for example. And by the way, each power term, right? Basically you increase the dimension of your problem, and start with the simple, for example, only x, right? And try to get a result, try to generate a Lyapunov function. If you constantly get infeasible problem type of error, right? Yeah, then move on. And by the way, you should be, you kind of, if you are trying to prove that your system has a Lyapunov function, meaning your system is stable, before that you should run a bunch of simulations, and you should see that, yeah, the convergence, right, is occurring. So there must be a Lyapunov function, and meaning the system, nonlinear system, is stability in the sense, has the stability in the sense of Lyapunov. Okay, and yeah, if you're sure that your system is stable, then move on to this step. Okay, let's say you did one sec. Okay, we were talking about two-dimensional, right? X1, X2 means it, right? Okay, and you failed, right? But you know it must be stable, so you should be able to kind of get a Lyapunov function. Of course, I'm omitting a bunch of mathematical, pathological cases, right? Of course, and let's focus on let's add, or let's increase the dimension of our problems, right? X square terms, right? Or the 2-degree terms, x1 squared, x1 times x2, right? x2 square, right? And then by the way, again, this is for two-dimensional, right? Let's say we again failed, but we are 100% sure. We would in that case add x to the 3x cube terms, right? Let's start from the top. Okay, x1 cube, right? 1 square, x1 square, x2, x1, x2 square, and x2 cube. Okay, and in that case, okay, let me just make a simple calculation. In this case, 2, 3, 4, right? You would need 9 by 9 P, this is the P matrix. Meaning you would need 81 parameters. But there is a catch. That P matrix must be symmetric, so you are not going to need 81 parameters, but you know there is 9 by 9 matrix, right? And 9 times 9 plus 1, 10, or 2, right? 45. You will need 45 parameters to be able to parameterize your Lyapunov function such that it is easier for you to represent your Lyapunov function in a SOS. Okay, function. All right. So let me delete all of them. And I'm going to I written a bunch of stuff before the video recording. And okay, so we kind of get this point, and for your V to be a SOS function, okay, these are the indeterminate. It is called. Wait a minute. Indeterminates, right? This type of terminology is pretty common in SOS programming, right? Optimization. And here you need to find your P matrix, and for that the condition that you like to impose on P is this: P being positive semi-definite. Okay, and if that happens, you are going to guarantee that your V of x will be sum of squares. Okay, and yes, this is required for a V of x Lyapunov function to be SOS. All right, and after that, what was the other condition? V dot being less than or equal to 0, right? Okay, and how would you compute V dot this manner, right? And for that, yeah, there's a catch. This is the kind of critical part. It kind of gets ugly, I will say, right? It kind of gets kind of confusing. All right, so far, and that's why I included a really good example, simple but kind of gets the point across, right? And here you have V, and V, you can think of V as parameterized by X and P, right? x1, x2, p11, p12, dot dot dot, right? X and p terms, right? Let me just put it in semicolon, okay? And to differentiate those terms, and here you are going to this is, yeah, this is v, and from that v you are going to find v dot, and again v dot will be parameterized by x and p, okay? However, you just computed v dot, and you have, for example, v dot equals, let me just write this way, p times x, let's say, okay, this is like will be the simplest case, right? P dot x, okay, and for your v dot or minus v dot to be SOS, right? And this term must be SOS. And again, what did we do in the first place? We just represented v of x such that it would be easier for us to represent v of x or parameterize v of x to be a SOS function, okay? And we are going to do the same thing, right? We have v dot, and now the interesting case here is this. In the first place, v of x was only a function of x, right? But now we have minus v dot, and here this, right? Minus v dot, but minus v dot is parameterized by x and p, okay? But we want minus v dot to be an SOS. So again, we are going to parameterize this, and to parameterize, we are going to again use basis functions, like, you know, this was the basis function that we use for v of x, right? And we are going to use another probably higher dimension of basis functions because of the reasons that I'm going to explain you. And actually, this is not a big reason. I mean, we are just going to multiply it with f terms, and since f terms will include x1 squared plus x2 or something, right? That kind of terms, and this type of terms will increase the dimension of our polynomial, right? Minus v dot. So probably, I mean, it might be the case the dimension of m2 and m1 be same, right? But like 99.9% of the time, m2 will have a greater dimension, is what I'm saying, okay? And so here we have this expression, and this is parameterized by p and x, okay? I'm repeating myself just to make it 100% clear, right? And for that we are going to employ another matrix called Q, like in the linear Lyapunov function, right? We are going to employ another matrix Q, and at this second I feel like somebody in the viewer is thinking, hey, why don't we just use P, right? I mean, but there is a reason why you wouldn't like to use P directly. Or what I'm saying is this, okay, you have, and let me explain, okay, x1 squared plus 5 x1 x2 plus 9 6x1 x2 9 x2 square, right? Okay, so I mean, this sounds like a SOS, right? But we don't know this, right? So we are going to like parameterize this, right? And we are going to write P11, P12, and P12 again because it's gotta be symmetric, right? P21. Okay, and then we are going to impose some constraints on this P matrix, right? And P must be positive definite for this polynomial to be SOS, right? Okay, so what are those constraints? Let me just write this. Okay, and let's just write this. Let's expand this, right? Okay, P11 times x1 square. Okay, plus 2P square x1 x2. All right, P21 times x2 square. Okay, so we are going to impose some constraints, and I kind of feel embarrassed because didn't give the whole picture, but let's say okay, what are the constraints? You can easily see, right? Okay, x1 square term and x1 square term, their coefficient must be equal, right? P11 must be directly 1. All right, and maybe it would be better if I use non-symmetric, but non-symmetric would be, yeah, no bueno. So let's use the P x1 times x2 terms coefficient 2 P12, right? 2 P12 and goes 6, and again 9 P21. And okay, I'm going to be honest with you, that didn't that wasn't a good example, but let me wait a sec. Yeah, let me get some good example. One sec. Hello again. I just look at the Wikipedia page and I see a really good example. And okay, let's focus on this polynomial. Okay, and if you were to prove the SOS-ness of this polynomial, you would probably start by checking the degree, right? And the degree is 4. Okay, and then you would calculate half of that degree and scale it up, right, or round it up. Okay, and you would, for example, if you had 5 the degree, right, you would use the basis functions, right? 5 over 2, 2.5, and round it up 3. Means you would need 0, 1, 2, 3, or the x terms, right? Or x1 and x2 terms, or x1, x2, and x3 terms, right? Depends on your indeterminates, right? And okay, we just calculated and it is 2. So we are going to employ 0, 1, and 2. Normally, this is what we would do, right? However, this, okay, let's not say anything. Okay, let's just construct this M matrix again here. M matrix being constructed, right? And we are going to find a P matrix, right, such that it is positive semi-definite, right? And first, to impose the coefficient matching constraints, we are just going to expand this x or M transpose P x expression, right? And starting from P11, right? P11 times 1. Actually, it's 1 times 1, but 1, okay. And then, okay, 2 times, because it's symmetric, 2 times P12 times x1. Actually, again, it's x1 times 1, right? Because it's, this is 1 comma 2 entry, right? 1 comma 1 and 2, first and second entries, right? And that's why the terms are 1 times x1. Okay, so here 1 comma 3 entry is, and since this is symmetric matrix, 2 times P13, right? And then what are the basis terms corresponding to that? 1 comma 3, entry 1 and entry 3, right? Okay, x2. All right, and you just continue, okay, and iterating over this matrix, and the final term you would calculate E66, not 2 because it's on the diagonal, and okay, 6 comma 6, 6 and 6, right? So x2 to the x2 square times x2 square, okay, x2 to the 4, okay. And if you, however, we will write this, and from the okay, you write this, right? And then you are going to impose the term coefficient constraints, okay, meaning you are just going to determine the coefficients of that polynomial, okay, and match them to the original polynomial. Meaning, for example, x1 to the 4, right? The coefficient here is 1. So here you are going to look at your generated new polynomial, and let me just think about this. You will probably need x1. I'm looking at this. One sec. You don't have, yeah, you can only do this by employing x1 square times x1 square, right? So, and x1 square is like here, e22, right? So yeah, and e22 must be 1. For example, this is like your first constraint, right? And I'm looking at the second term, x1 squared, right, x2 squared, and you can do this by, I guess you can do this only, yeah, x1 x2 times x1 x2, yeah, there is no other way, okay. You cannot generate this in other way, right? Okay, so x1 2, like this term, and this is the fifth entry, meaning 5 comma 5 entry, and that would be e55, right? Okay, meaning e55, or rather let me just write here, p55 would equal to minus 1. All right, this is your second constraint, and here e not p x2 to the 4, right? And you cannot generate other than using this base functions, right? And this is the sixth entry, right? And 6 comma 6 entry, p66. So am I making a mistake? I'm really like, okay, yes, yes, that's that was my logical fallacy. Yeah, I said it that you can, right, you can generate this x1 x2 and x1 x2, right? This is a one way of doing it. However, and this is like the most critical part, you can also generate this using x1 squared, and since we have x1 square and x2 square terms in our base function, right, m function, and x1 square and x2 square means you cannot just say e55 is equal to this. No, No, sir, you cannot do that. And you cannot do that because, let me again try to, explain that. X1 squared and x2 squared. Okay, two ways of doing it. X1 x2 times x1 x2. All right, and what are the entries corresponding to that? 5 comma 5, right? And p5 right? Okay, all right, diagonal term, right? And x1 squared times x2 squared. You can also generate using those terms. So what are the entries? What are the entries? And 4 comma 4 comma, I'm looking at this, and 6. All right, what is the term? P66, not P6. Wait a sec. No, yeah, P46, right? Am I making a mistake? No, P46 comma P64. Okay, so you can generate, or since you have this term, that means you can have P55, P46, and P64, right? Okay, because you are able to generate using those two terms. Okay, we didn't do the same. And let me just say that, for example, or rather, okay, so since I made a mistake, it is better for me to just explain on that, right? And expand on that. For example, we have x1 to the squared and x2 squared. Okay, this term, right? And the coefficient is -1. All right, you can generate this. I'm going to explicitly write that, right? E55, right? E55 times x1 x2 squared. Okay, plus, not, we're not done, plus 2p46. Okay, and I'm going to write this even with more information, right? X1 square times x2 square. Okay, means -1 equals e55 plus 2e46. Okay, this is your, and I made a mistake, sorry about that. And this is your second constraint, right? Okay, what was your first constraint? Let's check that again, right? The coefficient 1 times x1 to the 4, right? And looking at this, and please look at them really, pay attention, because it's really easy to make a mistake, right? Because you, one time you think, hey, you can just generate them using those terms, but also you ignore some terms. And especially for the large, or even in the small dimensional problems, you get some type of infeasibility errors, right? And okay, you can generate x1 to the 4, right? And only x1 square times x1 square. There is no other way. Okay, I'm 100% sure. Okay, for the second term, I wasn't sure, but I made a mistake. But okay, but for this, okay, that's the case. Meaning x1 square, and here x1 square is e4 times x1 square equals minus x1 to the 4. Write this better. E 4 here, because right, times x1 squared times x1 squared equals here, I'm looking at this, 1 times x1 to the 4th, right? Okay, meaning e4 equals 1. This was our first constraint, and let me just delete them, have a space. And okay, so what is the third constraint? Okay, you can generate x2 to the 4 again, like in the first constraint, only using x2 squared times x2 squared basis functions, right? And what is the matrix entry that corresponds to those term, right? x2 squared, meaning okay, what is the index number? 6, right? Okay. 1 2 3 4 5 6, okay, meaning e6 right? And e6 times, okay, again e6 must equal to, right, equal to 1. This directly constrains p6 term, right? And we have only one degree of freedom, is kinda the point here. And if you look at the terms, and let me just, for example, in the Wikipedia page, it directly shows this, but you don't want to do that. You just go step by step approach, right? For example, in P11, P12, no, P22, P32, P44, P55, and P66, right? Okay, so you have this term, all right? You have this term, all right? And you have also P46 and P46, right? Okay, and the spaces kind of represents that there are zero entries over there, right? And you have also P55, okay, and you, at this point, you will just look at the diagonal starting from the first one. Okay, look at this diagonal, and by the way, the ones that I haven't circled are 0, so in that P11 is 0. Okay, I just written them to indicate their locations in the matrix, right? All right, P11 is 0, and whole column of this matrix where P11 is included, right, is also 0, and also whole row that P11 is included, right, is 0, meaning we are just going to get rid of this. Okay, then we'll look at E22 term and 0, right? Maybe I should use blue color, right? We would differentiate it. Okay, this is 0 volume, and this was 0. P22 is 0 again. I mean, you can do that after you just get rid of the P11 reduction. Okay, let's consider, or let's imagine that you get rid of the P11 part, then you have this small matrix, right? Imagine that, and after that, again the first entry would be P22, right? And the column that is where P22 is located is all 0, composed of 0 entry, right? And P22, again the row where P22 included is all composed of zeros. Okay, and finally this will be the final, right? P33 after getting rid of P22 weighted. I mean, I'm 100% sure there must be a good term like representing this and this for a matrix, right? But I can not remember right now. And let's look at P33, right? Term entry P33 entry, and again this is 0, and whole column is 0, and whole row is 0. So the smallest matrix, right, we'll get is this. Okay, and the basis terms that corresponds to that little matrix or smaller matrix are this. Okay, all right. And for example, P11 or first entry 1, right? Entry 1 is, you just get rid of that entry 1, and entry 1 here is 1, right? And P22, we get rid of that P22, or entry number 2 is the term that we need to get rid of, right? And entry number 2 here, x1, right? And again P30. I'm explaining, I'm sure, in detail, but just to make it get the point across, right? P33 0, we just get rid of that here, that section, right? And entry number 3 is P33, and entry number 3 is this basis function, basis term, right? We just get rid of those basis terms, right? Okay. Then after the reduction, we just have this. But I mean, I written in a representational way, but we know from the before calculations that we did earlier, these entries are 0. These entries are 0. Okay, so let me just look at here. Yeah, and this is 1, right? This is 1. Okay, and let me call P55 and P46, right? And okay, we have only 1 degrees of freedom. And for example, you can tune only P55, right? And for some P55 values, you would have non-positive, right? Non-positive matrix. But for some P55 number values, you would have this matrix to be positive, definite. Okay, and if you have that, if you find a P55 value, which is the value you tune, right? That means you find a feasible solution which lets you conclude that the polynomial that you started with is SOS. Okay, that was like the great detour. And after that, let's continue. And where were we? Let's check. Yeah, we just we parameterize our Lyapunov function using p values, right? P values. And after that, we, using those p values, we computed analytically, but probably in that case we would use MATLAB simple toolbox, right? Minus v dot, right? Okay, or v dot, you can say. And after that, we are going to again parameterize this v dot term, right? Here v dot using q, right? Q matrix, and again q matrix is, for example, for 2 by 2, q11, q12, and it must be symmetric, right? q12 again, q22, right? Okay, now I am going to start an example to explain this better. And okay, we just parameterize this using q, and at this second there is a connection between p terms and q terms, the entries of the p matrix and entries of the q matrix. Okay, but again we will have some degrees of freedom for the q. You can, I mean, there would be some cases where you don't have any degrees of freedom. You are bound to construct q matrix using only p, right? For example, you just have to use p or 2p12 or something like that, right? But in that case, okay, that's the end of the story. But probably, and like 100% maybe, you are going to have some degrees of freedom. Okay, remember the example. We know the parameters. For example, parameters were 1, -1, and 1, right? And let's think of these coefficients, this numerical 1, -1, and 1. Let's think of it as p1, p2, and p3, right? Right. For example, let's think of it like, I mean, yeah, since, okay, I can write this, okay, p1, right, and p2 and p3, for example, and let's think them as q1. I am really hoping that you are able to see that. Okay, and q1, right, q2, q3, right, okay, and here q1, for example. And in that case, for example, q1, you know this q1 is just p3, right? You don't have any degrees of freedom from this constraint. And here q1 is p1, so again no degrees of freedom. However, using that constraint, that means if you have p2, you can use two q terms, meaning let me just write q2, right? Otherwise that will be illogical. Okay, and in that case, I mean, again, 100% being not 100% correct, but you kind of get my point. p2 terms doesn't directly determine q1 terms. You will have that, and that means you will have some degrees of freedom from q matrix, okay, from q terms. All right, okay, and even for this really easy example that you're going to see what I'm saying. And okay, where are we? Okay, we are just going to parameterize them, and we are going to determine the relationship between p matrix and q matrix, okay, or p entries and q entries, right? Okay, all right, that's the end of the story. That's the end of the general explanation. And now we are going to embark on a journey where we explain or explore some examples, right? And here, this is the nonlinear dynamical system, where, of course, this is linear, by the way, but let's not focus on that right now. And let's or pretend that that was nonlinear, right? Okay, that will be I mean, you are going to see the calculations will be much cumbersome, right? And then we are going to deal with right now. So okay, and some bird told you that, hey, use this basis functions. You don't need to go to the second order terms, third order, etc. Right? Just use first order terms, and you're like, okay, whatever. And then this is the v of x, right? This is v of x. All right, and you just parameterize your Lyapunov function using p values, p11, p, right, where p22, and this is again symmetric, and you have 3 parameters. If you know these parameters, that means you know your Lyapunov function. Okay, and you just expand your Lyapunov function in terms of, again, p values. All right, that's the first calculation, first stage. After that, you need to calculate analytically v dot. All right, v dot, again, remember what is the expression for v dot, right? All right, and now we are going to really do the analytical calculations. Here, let's just do that. Gradient, or rather, you can write this, right? Okay, and if you have two-dimensional system, and we have right now, right, transpose. All right, this is it. So here you need to calculate this. And what is the Lyapunov function? Here, this is the Lyapunov function, right? And for that, e11 e x1 squared, right, plus 2. I don't have to write this, but here derivative of this term with respect to x1 is, you can just write directly 2p11, right? I'm looking at this like, yeah, times x1, right? And after that, from this term, you are going to have some term as well, and this is 2p12 times x2, right? Derivative of this term with respect to x1. Okay, write this. We found this, right? Okay, all right. So let's find this. Again. Derivative of this term with respect to x2 is 2p12 x1 plus derivative of this term with respect to, right, with respect to x2, 2p22 x2, right? Okay, and again, this is the same term that we calculated earlier. And okay, so we just computed this, and let's write down our f terms are here, right? f1, f2, right? Okay, f1, f2, and I just written f1, f2 explicitly, right? And at this second, let's just stop and really compute v dot term in terms of p terms, right? We are just going to multiply this term with this term, right? Okay, this will be the t1, term 1. Okay, here t1, right? This term and this term and this term is this, right? f1, right? Okay, and this is it, right? And you just do the FOIA, right? And you will get these 4 terms. You can just stop and check the calculation, right? You are just going to get these 4 terms. Okay, again, f11, f12 or something, you can just think of them as numbers, right? These are the things that we know, right? And again, remember, this is just to get the point across, and this is a simple example. I am aware of this, right? And okay, but it's a descriptive example that really would help you to understand. And okay, again, this term, we are going to multiply this term, and that will be our term 2 to construct v dot in terms of p, right? And here this term and this term, right? And again there will be this four terms, right? And okay, yes, so we have these 8 terms, and now we want to prove the negative definiteness of this, right, of this large polynomial. And remember, this is like two-dimensional example and very simple example, and even that you have like 8 term, right, v dot with 8 terms. So you can consider, you would imagine you wouldn't do that and computers would do that. And to prove that type of negative definiteness, you are going to parameterize this using q, right, q terms. In other terms, not the p terms, if the q terms are bound to be determined by only p terms and no additional degrees of freedom, that will be a really simple example, and you are not going to bump into those, I'm imagining, right? And okay, and after calculating v dot in terms of p terms and having these 8 terms, right, you are going to, using this, right, expand this v dot, and I call it v dot SOS because it's like SOS representation, right? And so what I'm trying to say is this, these 8 terms and these 3 terms are equal. All right, what does it mean? It means this, we are going to, and let me just put it like this, right? We are going to do the coefficient matching, right? Coefficient matching. Okay, let's look at the coefficients of x1 squared, right? Since we don't have any, yeah, all of the terms we have like order of order 2, right? x1 squared, x1, x2, x2 squared, right? They are order 2. Okay, and all right, x1 squared, the coefficient is here, right, q11, and in these 8 terms, what are the coefficients of x1 squared? In this term, obviously, right, and additionally this term. So we are just going to write them over here, right, because we are going to do the coefficient matching, right? We are going to impose this type of constraint. And again, remember this, for example, let's think of f11 as 3 or something, right? A number, right? Using those numbers, we are going to impose linearity constraints on our p and q terms. Okay, all right, so let's check q1, I'm sorry, x1, x2, right? x1, x2 and coefficients, and this is the coefficients, right, in vsos polynomial, right? And here this is, right, this term, and this term, there will be 4 terms, right? Okay, we just written all of them here. And after that, let's check x2 squared, right? x2 squared terms here, this is it, and x2 squared terms, I'm looking at this, yeah, this one and this one, right? All right, just written down. So all right, after doing the polynomial matching constraints, right, and these are the polynomial matching constraints, we are going to also impose this positive definiteness and negative definiteness constraints, right, or positive semi-definiteness and negative semi-definiteness constraints, right? And again, remember these constraints as well. but since we haven't included constant terms in v of x, we just started from x, right? And dot dot dot, and this won't be a problem. I mean, this wouldn't be a problem usually, but you would like to really check. I mean, probably this would be a problem. You would need to make this or include this constraint in your optimization problem, right? For example, what I'm trying to say is this: v dot and e parameterized by p, right? Would have. I'm looking at this. E 13, for example, and x1 not squared x1, for example, right? So you would need to v dot might have some constants, is what I'm saying. Okay, and I'm looking at this right now, for example, and okay, 3 constraints, right? 3 constraints, and I just written all of them explicitly. Okay, here let me just get this name of the constraints here so we can match them up, right? Here polynomial matching coefficients, matching constraints, and here polynomial matching constraints, right? And here e being positive definite and q being negative definite, right? And yeah, for that we haven't written explicitly, but these are the also constraints that will be included in our optimization problem. Okay, this is, yeah, this is the like end of the part 1, I will say, for this. Okay, and after that, now I'm going to focus on the other parts where we will talk about the linear programming. Okay, and here I kind of wanna delete all of them, but let's not, right? Let's just start over. Okay, so just let me write LP, linear programming, right? And okay, again, linear programming is a name of an optimization problem, and again we are going to parameterize our v of x, right? I'm going to call it m1 transpose x p, right? m2 x. Okay, all right, and you want this polynomial to be like this, right? Okay, and probably you would like to impose that constraint. You would like to see that, right? Not greater than and equal to 0, but just positive, right? Greater than 0 strictly, right? And okay, and you need to obtain p terms. All right, after that v dot, right? You are going to also times f, right? Transpose times, I shouldn't write this. Okay, so what is this? This is, for example, what is this? M1 transpose E, right? Why did I write this? Okay, this will be M1 again, right? M1, right? Okay, and this. Okay, you can think of it like ex square. So in that you would have 2p and 1x, right? And you are going to 2p and 1. I'm looking at this. Okay, just one sec. Okay, by expanding this term, you are going to get this, right? Meaning something depends on p and x, right? And by the way, I'm looking at this. Let me like show it like this, right? That expression. Okay, and the problem is this. This depends on p and x, and we want it to be represented by m2 basis functions, right? Q and m2, right? And where q is less than 0, and so this is, I mean, this is the kind of critical part. V dot here, V dot, the, I'm gonna call V dot P, okay? Okay, that will be make things clearer, I guess. V dot P, right? Okay, we just computed that, and this is V dot P, V dot P, right? And this is the expanded representation. Here again, remember that m1 x, for example, we only, or we included x and x squared, right, in our m base function, and derivative is 1 and derivative is 2x, right? Okay, meaning we are going to get another x terms, and here x terms again, right? And okay, having done all this, having calculated v dot p, right, we are just going to vq dot, okay, m2 basis terms, right? Q and m2, right? Okay, and then we are going to decide which m2 or basis functions to include in m2 term, right? After that, we are going to again, I'm gonna write 10 this v dot q terms, and as a result of this, we are going to have a polynomial v dot e, where we have e11 times x, I mean some p terms and some x terms, right? Some p terms times some x terms, dot, and it will be a really large big polynomial, right? And many terms, right? And here v dot q polynomial, here again we will have q11 dot q1 squared, some q term, some x term, plus some q term, some x term, right? Dot, and then we are going to make the coefficient matching, right? We are going to generate the equality constraints using those coefficient matching stage, right? This coefficient matching stage, and of course YALMIP or another whatever the optimization toolbox that you like to use will be doing that, not you, thankfully, right? And that optimization toolbox will generate bunch of there will be maybe hundreds, right? Bunch of constraints. Your optimization toolbox will generate that constraints using those v dot e and v dot q equality, right? And all right, so the problem is this at this point: find p and q such that p this, q this, and right. Okay, and here for the LP technique, it is very similar. So let me just think about this. You are not going to consider the q terms. Okay, I'm going to expand on this for 1 second. All right, so you have like only starting from v of x, right? You have p terms. Okay, that's perfect. And what is the condition? V of x just must be positive, right? All right, so you are going to write expand this. You are going to expand this, right? Dot, right? Some p term, some x term, some p term, some x term, right? You are just going to expand this, and you are going to generate here. This is like consider two-dimensional state space, right? And two-dimensional state space, and generate in a, for example, you can decide, by the way, and it depends on your choice. Let's consider some R ball, right? You will generate bunch of, just going to write, just generate bunch of, right, points in this, like thousands maybe, right? Bunch of points in this ball, right? You can just generate uniform distributed PDFs, right? All right. After that, and people write like this: m1 xi, because, for example, I will be from 1 to n point, right? Maybe 1000, for example, right? And you are just going to get some xi, for example, i equals 1, xi will be like 0 0.1, 0 0.3, for example, right? This kind of is something that I'm talking about. And okay, so what is this at this point? For example, x1, x2, x1 squared, x1, x2, x2 squared, right? And if you know xi, right? For example, x1 equals 0 0.2, x2 equals 0 0.3, for example, right? You just sampled here, or rather here, you just sampled some xi, right, from state space in that ball, right, with radius r, and you are going to substitute and compute mxi. And what is this? This is just going to be a 1, 3 or something, right? 5. This is going to be a vector where you will only have numbers that you know, right? You just calculated that, It is not x dependent term anymore. This is just a constant vector, right? You can think of it right that way. All right, let's move forward. Okay, we were just talking about this, right? Okay, m1 xi, right, times p m1 xi. So what is this? This is going to be e terms times a number, right? E terms times a number, dot, right? Or for example, e equals 1, right? In that you just calculate it. All right, let's do little steps, right? I equals 1. Okay, you just sampled xi. You know what xi is, right? Okay, after that you are going to compute x m1 of xi, right? And this is a vector consisting of numbers, right? After that you are going to compute v of xi, and v of xi is m1 transpose xi times e. Again, this is this constant numbers. This is something that you know at this point. This is just numbers, right? Okay, weights, right? And m1 of xi, right? Okay, here in this term, the only thing that you don't know are the p terms, p entries, right? All right, and for each, and remember, these are like, for example, 5 times p11 plus 2 times p12, right? 3 times p33, right? These are all linear constraints, is the kind of the moral of the story, right? These are all linear in p terms, and this is great news. This, you have no idea if you are not aware of this kind of optimization. This is like the best optimization, like the most easily solved type of optimization problem you can ever get, right? After this class, I guess. Anyway, and this was for I equals 1, right? And dot dot. Okay, not dot dot, right? Let's do it for I equals 2. All right. Again, you are going to sample some xi, for example. Just sample it, and we get xi equals 0.1 and minus 0.2, for example, right? We just sampled it. We know this. Okay, we just generated not random and uniform distributed from uniform distributed PDF. We just generated at random, and in that given sphere with r radius, right? And again, we are just going to compute m1 of xi, and this is again numbers, okay? And after that, we are just going to compute this, right? Okay, I'm doing annoyingly repetitively, I'm aware of this. Okay, so just bear with me. And again, this is again a some p term, some p terms, some number p terms, right? Some number, but however, for e equals 1, right? You have some weights, right? And for e equals 2, you will have other different weights, right? This is different. So you are just putting constraints after constraints. You are just basically through sampling the from that R ball, right, from state space and imposing the positive definiteness of Lyapunov function constraints, you are just generating constraints that you are going to impose on p values, right? Okay, this is what I'm saying. All right, after that, again, you did this for dot 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 I equals endpoint. And by the way, npt endpoint must be like, of course, more than 100. I mean, for even for the smallest easiest problem you might have. However, this might be like thousands, right? In the order of thousands, 10,000, right? 2,000 or something. And again, the same thing, and again, same, right? So you will have like n linear inequality constraints, right? Okay. After that, you are going to just compute v dot, and here you will probably going to use matlab sample toolbox, and here in this you will have some p term, some x term, right, plus some p term, some x term, right? And you know, I feel like you know where I'm going with this. Okay, and this is v dot, and we know v dot must be greater less than 0, right? Okay, and you know what, this is perfect. So we are just going to employ the same strategy. We are just again maybe use the same, not maybe, actually, yeah, we are probably going to use the same samples, right? Here, those samples, right? We are going to use same samples, right? From that, you're going to use that for I equals to, right? Get that sample, right? For that, not m1 of xi, you are just going to calculate v dot of xi directly, right? And again, you will have some p term, some constant, plus some p term times some constant, right? Plus some p term, some constant, less than 0. Okay, again, v dot of xi for different sample, right? Again, p constant plus p constant plus p constant less than 0. You are again impose those I equals and point, right? Again, those and inequality constraints, right? And point linear inequality constraints. All right, and all right, so far you have 2 times n point, and for n pt equals 1000, you will have at this point 2000 inequality constraints, but remember they are all linear, right? So it's okay. And again, finally, you are just going to impose that constraint, right? For that, again, you will have, let's remember what v of x was, right? Some p term, some x term, plus some p term, some x term. And by substituting x equals 0, right? You will have, I mean, v of 0 equals 0 is kind of the constraint that you satisfy directly, right? But yeah, it kind of means you will not have some p times 1 expression term in this v of x polynomial. All right, but remember that, okay? And after that, no constant terms in, no only p dependent terms in v of x, okay? And let me delete that. After that, v dot of 0 equals 0, and what was v dot? V dot equals p, right, times x plus p times x, right, v dot of x, right, and v dot of x, substitute x for 0, right, and you will have p. Again, no constant, for example, if you had like p55 or something, or p not, yeah, you might use p, that kind of index notation, p55, right, times 1, right, that would mean p55 equals 0, right. Directly you would decrease the dimension of your problem. You would get rid of 1 degrees of freedom. That means, okay. Alright, so I'm going to delete all of them. Give me a second, right? And okay. Step 1. Just express v of x in m1 transpose x e m1 of x. Okay. 2. Generate samples, right? xi from the ball with radius r, right? And by the way, this type of Lyapunov function construction is also, it has some additional benefits than the SOS. I mean, SOS method that we covered in the previous video, but of course I'm going to expand on that SOS method of constructing Lyapunov in the future videos, hopefully, right? And okay, maybe I will mention that. What I'm saying is this: you can use, for example, you just pick the ball, right, with radius r, okay, and you just picked, right, you just draw a bunch of samples, all right, and you just have constructed v of x greater than x for x not equal 0, and v dot of x less than 0 for x not equal 0. By the way, let me just follow x in br, okay, in this ball. This is, for example, it is not, this v of x is only, and let me write this here, okay, for example, one sec, just give me one sec, okay, only greater than 0 for x in br excluding equilibrium point. However, we cannot guarantee all of x not equal 0, or rather that would be, wait a sec, in Rn excluding 0. This is not the case. This is only locally. This condition, right, this condition is only valid inside of this domain. What is the domain? The domain is the ball, right, with radius r, okay. And you're like, what is the benefit of that? This has a great benefit. So, for example, you can prove, I mean, let's consider you have two equilibrium points, right, and one is one instability with instability, right, or maybe one with stability, right, one with stability, and again the equilibrium point 1 and equilibrium point 2 are stable, right. For example, this comes right there, right. So for the result is this: with non-instant, with only two stable, maybe more, I mean, more than one stable equilibrium points, you will not have a you couldn't generate a Lyapunov function to prove global stability because it is not globally stable, right? It is only, for example, stable in this ball or in this neighborhood of that equilibrium point, right? Maybe ellipsoid or something, right? And okay, so if you have one equilibrium point and it's stable, you have the ability to prove global stability. But most often you will have more than one equilibrium point, stable equilibrium point. So you would like to use that type of strategy, right? I mean, generating local, and this is like the keyword here, local Lyapunov functions, right? Or Lyapunov function that is only valid, that only satisfies our general Lyapunov constraints in this region, right? In this region, but we cannot say more than this, more than outside of this neighborhood. And you are kind of familiar with this, I feel like, if you're watching this video, because in nonlinear dynamic systems, right, in that, if you got that kind of course or if you read some bunch of stuff, by the way, I gotta check the name, but Steven Strogas, right, there's a really good YouTube video course online, right, and he covers nonlinear stability and chaotical aspects of nonlinear systems, right. That was a really good example and good lecture. I would recommend you to watch, right. And also second, NPTF, of course, NPTF, if there is a course, there would be an NPTF course as well, right. Okay, and there was more than one, I guess, maybe more than two NPTR courses related to nonlinear systems, nonlinear dynamical systems, right? And okay, and I'm thinking, yeah, there would be some other nonlinear dynamical systems related courses on YouTube, but I cannot remember at the top of my head, right? Anyway, for example, yeah, in nonlinear dynamical systems, what do you have, for example, that you wouldn't have in linear systems? You would have stable oscillations, meaning, or aka limit cycles, right? One unstable equilibrium point, right? Here converges to that limit cycle, right? Here, this is a limit cycle and comes from here. The points outside of this limit cycle also converges, and then you will have a limit cycle. All right. So in that, if you have that type of systems, right? Good luck finding a Lyapunov function to prove global stability, because here's the news: it's not global stable, right? And what you like to do in that case, I will make a mess. All right, all right. This is the, and you know what? Let me just do like this, like really ugly, right? Not symmetric or not perfect circle looking limit cycle, but this is like the more realistical, I guess, limit cycle, right? All right. For example, this is a unstable equilibrium point, right? And converges to that, right? And you like to kind of estimate the location of your the inner circle region, right, of your limit cycle. Maybe you are interested in the question, how big of a circle that I can place inside of this limit cycle, right? What kind of area are we talking about? And in that case, and remember that it's like unstable, so you would for example, x dot equals f of x, right? You would use x dot equals minus f of x, okay, because you would like to inverse to, or the reverse to dynamics, right? Okay, this is for minus f of x. All right, now you have a stable system. This is like the system 1 and this is like the system 2. So now you have the ability to prove a local asymptotical stability, or local stability in the sense of Lyapunov, right? So here you are going to select a ball. By the way, this might be done in a bisection way, right? You will start with like simple little, small ball, and then you will make it larger and larger until you get some type of, until you kind of touch to the boundaries of that limit cycle, right? And for that, for example, this is like R, right? B sub R, right? Ball. And here again you are just going to employ the same strategy at Lyapunov function construction using LP, right? And okay, this is it, I guess. And after that I'm planning on also including YALMIP, really good YALMIP examples. And okay, I'm checking, by the way. Alright, now I'm going to just say a couple of things about the next examples. And first, LP, YALMIP, and Lyapunov, my just, yeah, writing just got worse. Okay, Lyapunov function construction, right, or computation, and matlab example. This will be a matlab examples. And two, SOS, again YALMIP. This will be YALMIP examples in matlab example, right? Matlab Lyapunov function. And after that, I am considering to use or to represent some SOS techniques to, I mean, SOS is really interesting because there are some SOS techniques that would let you to find or determine a global minimum of a non-convex polynomial function, which is like really good news, because I mean, if it is not convex, right, that would, and if you are using like Newton-Raphson or that type of gradient descent type of computation, that means you would stack in a local minimum but not the global, right? And so the question of determining a, let me just expand on this question of determining a, right, determining a global minimum is very important. And for example, this is f of x, for example, right? And in that, and this is like the gamma, right? I'm just going to spoil it for you because that will be in the next videos, I guess, right? The problem will be minimize gamma, minimize this, or rather maximize gamma, right? Just improve, just make bigger gamma every time, right? And such that f of x minus gamma is SOS, right? And yeah, you are just going to use that type of approach. And I mean, when I first heard this, that really surprised me. So I find it really valuable, and I'm going to do some example video regarding this problem, and maybe you will need it in somewhere, and maybe you need it and you don't even know that you need it. Okay, and after that, this is like one, right? And after that, p of xy and p of xy and xy, or rather 1 x y x square xy x y square dot dot dot, right? Again the same right? X, Y, X squared. Finding a Q such that finds Q such that M of X Q equals P of X, and you think of it like X and X as a XY, or maybe X1, X2, X5 or Xn, right? Think of it that way and find Q such that this constraint is satisfied, and Q, and we know that P of X is like positive, Q is positive, and this is another problem. This I really want to make a video about, right? And the third problem will be P, not like small p, like this, like capital P, right? X. Again, when I say X, you can think of it like XY or X1 to the Xn, right? And here, this is the hard example because P11 X, right? P12X, P21X, P22X, right? And for example, let's think of it for two indeterminates, right? X squared plus Y squared, right? 2xy, and X squared plus 2xy squared, right? And 3x squared plus 5y squared plus 3xy, right? This type of, I mean, a matrix whose entries are, right, polynomials. Not even polynomials that depends only one indeterminate, but maybe more than one, right? In this case too. So, and SOS decomposition of polynomial matrices, right? Okay, poly matrices, and this is also some problem that I find interesting. I haven't used to solve a specific problem, but I find it really interesting, and I'm going to do a video about this, right, in the next days hopefully, right? And okay, that's it folks. Okay, thanks for watching.